In this segment, we're going to talk about a little bit of LSTM visualization in order to try to get a bit of a better idea of what these can do in language modeling contexts. So this is some work due to Andrei Karpathy et al. From Stanford in 2015. And the thing they did was train a character-level LSTM language model, so predict the next character based on the history, over two corpora, War and Peace and the Linux kernel source code. So two very different sources of text here, one not natural language. And what they did was they looked at the individual components of the cell state C in order to understand what was going on. So they looked at the activations of it and basically plotted them over different time steps in order to try to understand the behavior. So what we see here is an example from War and Peace, not the Linux kernel, where we have isolated one particular unit, one unit's activations, and kind of color-coded them where blue, I believe, is low values and red is high values. So what this shows is that this unit does something and kind of has a particular behavior in the context of this LSTM. And so if you look at what the context is actually doing, I'll give you should be able to spot that basically it seems to get high values towards the end of a line. And so this unit is basically acting as a counter. And the reason we might need a counter is that the way their data was formatted is it actually had new line characters in it. And so in order to figure out where to generate a new line character, we would need to know how many, essentially how many characters we've generated so far, and this unit seems to be able to do that. So this is actually something that comes up a lot in machine translation. People have looked at this there as well and found that there are some units that when you're translating a sentence that the unit kind of goes along and then it like spikes when you get to, if you're translating a 30-word sentence, like once you've produced kind of every word, it spikes, and then that usually triggers your decoder to end the sentence. So this is something that's going to come up when we get to machine translation, and is a very useful property for LSTMs to be able to have for that. All right, here's another set of activations, which I'll give you a few seconds to look at. So we can think about what this one is doing as well. And what you should be able to spot is that this unit is basically acting like a kind of binary switch to tell us if we're inside a quote or not. And so the idea is that the distribution of language within a quote probably has a lot more things like personal pronouns, for example, I, etc. And so this switch is generally going to be a very useful feature for a model to know what character is probably coming next. And so this is something that the model seems to have learned from this data. Here's one from the Linux kernel. And what's going on here is that this unit appears to basically be acting like a sort of stack. Its activation is higher at sort of greater levels of indentation, and this probably reflects the fact that at outer levels you'll do things like declare and initialize loop variables more, and maybe you're unlikely to have 6 nested for loops. So once you're inside a few levels of nesting, you're likely to have a different distribution over statements. All right, here's another one. So this one, if you can figure out what it's doing, you get some sort of prize, because this one is not really super interpretable. The way we kind of talk about a unit like this is it's probably doing some kind of double duty where it's modeling a few different phenomena at once, or it only makes sense in the context of other activations. For example, maybe it's the case that unit 71 plus unit 473 when you add them up and subtract this unit from them, they give some kind of reasonable and interpretable pattern. But when you just look at this unit on its own without thinking about it as a residual from those other units, you have no way of understanding what it's doing. So this is the kind of thing that can happen when we interpret neural networks. And this is something that makes it a little bit hard to understand what these different activations are doing. So it's remarkable that Karpathy et al. Were able to find these kind of patterns, because usually you get stuff like this. And even if the system's behavior is pretty good, a lot of times, even in something like a linear model, we're not able to fully unpack, like, okay, why did it make this prediction? Well, this feature looks high and this feature looks low, but there's so many other features that collocate with those and are sort of have correlated weights that usually it's a little bit hard to figure out. So we'll look at some other interpretation techniques for neural nets later in the course that are going to allow us to try to kind of peek inside and understand what they're doing. But for now, we could see that these sort of stories we were telling about what LSTMs could do in terms of looking at the input and forgetting and remembering certain things and having these different behaviors do seem to be borne out when you train LSTM language models. And the final thing I'll say about this is that what this shows is that language modeling is in some ways a very powerful task for driving what a network can learn. For example, we were able to learn the notion of like quotation from just trying to predict the next character. And so this is going to be a key notion when we get to pre-trained models and start thinking about how language models essentially drive building good contextualized representations and pre-trained models that can do a wide variety of tasks involving language. That's it for this segment.